Let us consider a simple security game model where two patrollers have to defend some targets from an attacker. We want to find the max-min strategy of the team formed by the patrollers against the attacker. The graph in picture represents a schematic map of the environment. The two patrollers are initially in position D1 and D2, respectively. The targets are in position T1, T2, T3, and T4. The game goes on as follows. Each patroller selects a target to check, while at the same time the attacker decides where to attack. If one of the patrollers chooses to patrol the target being attacked, then the attacker is caught and patroller's utility is 1 and attacker's 1 is 0. Otherwise, the attack has success and player utility is 0.5. This is the normal for representation of the game, where the attacker chooses one of the bimatrices, while the patrollers select rows and columns in the bimatrices. Only patrollers' utilities are represented. Those of the attacker can be obtained as 1 minus patroller utility. For instance, if at least one of the patrollers play action T1 and the attacker also chooses T1, then patroller utility is 1. Now let us write the ample data file. Call uppercase I the set of actions. In picture you can see how to write three-dimensional matrices in ample. Basically you must write each bidimensional slice separately. For instance, the part in red corresponds to the case where the first index has value T1 according to our convention, the case in which the attacker plays T1. The other parts correspond to the other values for the first index. Now let us run the model. The .run file is always the same, except that this time we use the solver baron instead of Gurobi, as we are dealing with a nonlinear program. This is the output produced by ample. As you can see, the max-min strategy prescribes the patrollers to uniformly randomize over the targets, one of them between T1 and T4 and the other one between T2 and T3.